Hello, my name is Hunter Gibson, and this is an R2R digital to analog converter, or DAC, which converts digital signals into analog voltages. The way it works is by using a simple network of resistors, R and 2R values, arranged in a ladder structure. Each bit of the binary input controls a switch that connects either to 0 volts or a reference voltage, depending on whether the bit is a 0 or 1. The resistors scale the contributions of each bit to the final output voltage. As you can see here, the output is a stepped voltage, which increases as more bits are switched on, producing the familiar staircase pattern. Here's a schematic of the R2R ladder with 4 bits. Each resistor in the network scales the input from least significant bit, LSB, to most significant bit, MSB. This structure works based on 2 important principles: superposition and Thevenin equivalent circuits. Superposition allows us to consider each input separately, and Thevenin's theorem simplifies the analysis by reducing complex parts of the circuit to a single voltage source and resistance. On this breadboard, I've prototyped an 8-bit R2R DAC. The dip switches allow me to toggle between binary values, while the resistors control the scaled output. As I change the binary inputs, I can measure the voltage output using a digital multimeter, which matches the expected values calculated using the formula voltage out equals reference voltage times binary value over 2 to the power of n, where n is number of bits. After building the prototype, I moved to EasyEDA to design a custom printed circuit board. This software helped me translate my breadboard into a more durable and permanent design. I positioned the resistors, dip switch bank, and op amp, ensuring efficient trace routing to replicate the same functionality as the breadboard. After finalizing the design, I ordered the PCB, soldered the components, and tested it to confirm the output voltage matched the binary input. To protect and house the circuit, I used Fusion 360 to design a custom 3D printed case. The case is designed to hold the PCB securely while leaving space for the switches and connectors to remain accessible. I added screw brass insets to secure the case with nylon screws, ensuring a solid and professional finish. Once printed, I assembled everything and mounted the PCB into the case. With the DAC now fully assembled in its custom enclosure, the project is complete. This combination of hardware and design skills has given me practical experience in both digital to analog conversion and in PCB and 3D design using EasyEDA and Fusion 360.